to the level in this row. So that's how you convert a categorical feature into a set of numerical features. Another very common data format is text data. There is another way of converting this data format into numerical vectors. This is a very common method used in natural language processing, and it's called vectorization. Vectorization can be achieved in many ways, but I will focus on n-gram generation. So an n-gram is basically an occurrence of n consecutive words in the text. So for instance, a bigram, so an n-gram consisting of 2 words, can be, for instance, be happy, just as shown on the slide. And by scanning through each message, we generate, we count all the n-grams that occur, and that's how we convert such a message into a numerical vector that we can later feed into our machine learning algorithm. So what are the possible obstacles that we might encounter using those techniques? Well, first of all, we have a very big feature space, because when you take into consideration all the n-grams, all the bigrams, for instance, in the English language, with over 1 million possible words, then you end up with 10 to the power of 12 possible bigrams, which is a huge number, and it's not really feasible to consider them all in data transformations and machine learning.
I just want to add that you might suspect that many of those bigrams are not really important, because in English language they just don't occur, but it is also very hard to say which bigrams should be ignored. For instance, if a message has a bigram which shouldn't appear in English, it may be a good indicator that it was written by someone who is not native English speaker like myself, or it means something else. So it is very hard to upfront decide what bigrams should be ignored.
Yeah, that is true. So there is no practical, easy way of trimming this space. Another problem is that when we come across new categories that were previously absent from the data, for instance, with our weather example, when we encounter a 4th level called windy, then we need to introduce a 4th column, so we need to basically change the data schema, which is a problem. If we, for instance, already trained some models, then we need to retrain them in order to comply with the new schema. So I'm going to show you one method that's recently become popular in dealing with such problems. This method is called the hash trick, and it works as follows. You feed each bigram or each category of each level of a categorical feature into a hashing function. And what this function does is that it maps this bigram or this category into an integer within the range between 1 and k, where k is a fixed number that we choose up front. For instance, we decide that we want to generate 1,000 features. So what we do is that we set k to 1,000, and then we map every possible bigram or category into an integer in the range of 1 to k. So what do we gain from this approach? First of all, we can greatly reduce the feature space, because we can choose k however we like, so we take control of the trade-off between feature space size and algorithm performance. Second, we don't have a problem with new categories anymore. So when we encounter a previously unseen category, this will be still mapped by our hashing function into a number in the range from 1 to k. So we only increment one of the features, and there is no need to change the data schema. Obviously, in this approach, some collisions will occur, because especially if k is much smaller than n, so the number of possible bigrams, say, or the number of categories, then we will have collisions, but this is usually not a problem, because empirical data shows that such collisions usually do not impact the performance of the algorithms in a significant way.
I just want to add that very often those collisions are very helpful, because they reduce the risk of overfitting. So in practice, it is desired to have that.
Yes, that is true. And if for some reason we do have a problem with collisions, then we may introduce a second hashing function that will convert the expected value of each feature to 0, and this is often something that's desirable. Okay, so now I will move to another subject. When dealing with machine learning on top of big data, we need to choose the right paradigm for this. And the most common paradigm is called offline learning. And in this paradigm, we train the model on a whole data set, on a whole available training data. So once we do it, we periodically redo this process and update our model that operates on production, so that after a batch training process, we need to move our model to a productive environment, and then this model begins generating scores by consuming a test stream. So that's the common approach, but there are some problems with that, especially when the data is very big. So first of all, our models are not able to quickly adapt to the latest trends, because basically at every moment we are dealing with a slightly outdated model. How slightly, it depends on our update period, but if this update period is, for example, a day, then there is never a model in production that has seen the latest data from the latest day. So it might be a problem in some applications.
An example use case here would be stocks exchange prediction or weather prediction, where you need to have the historical data, but the latest data are very, very important for you.
Yes, that is true. What else? We have a need for big computation, which directly implies high infrastructure cost. And in some cases, this approach is entirely not suitable, because when you have a significant amount of incoming data each day, then your training data set is growing, and if you want to retrain it each day, then at some point it might not be possible, because the training time would exceed your update period. So this approach is not scalable. An alternative approach is called online learning. And here the difference is that we don't talk about a training data set, but rather a train stream. And this training stream is gradually consumed by our training algorithm. So after processing each training example, the model is updated. And we always have a functional model in production that can respond to predictions. And this process begins from the first processed training example. Not every algorithm can be adapted to this paradigm. Some of them are well suited for this. For instance, linear regression is very well suited for this approach. In this case, it's called recursive regression. So we can easily improve our model gradually, piece by piece, after consuming each training example.
Let me just add one more thing. One day I was thinking about why linear regression is so popular, and very often it is much more powerful than more sophisticated machine learning models for big data. And my friend remind me a theory from calculus. It is called Weierstrass theory, and it basically says that every function can be approximated by polynomial. It's the question, what is the degree of the polynomial? So if you do the proper feature engineering, then linear regression becomes a really, really powerful tool.
Yeah, so that means that we can successfully use linear regression to general machine learning for the data that contains some nonlinearities, and that this algorithm is well adaptable to online learning. On the other hand, tree-based models such as random forests are not well suited for this, because we need to recreate the whole tree structure after adding new examples, because the structure is dependent on the training data as a whole. So what are the benefits of online learning? First of all, what we gain is the data size is virtually unlimited, because the training stream is consumed piece by piece, so the training algorithm doesn't really care where the rest of the data is, as long as it gradually gets the data stream piece by piece. Second advantage is that we obtain the first functional model very quickly after processing the first example we already have something. We do have a model that is functional. It may be very inaccurate, but it will gradually improve while consuming the training stream. So one tool that is worth mentioning in the context of online learning is called Wabbit. It is a tool that was originally developed by Yahoo and is now being maintained by Microsoft. This is a command line tool that uses out-of-core processing and the hash trick that I told you before. It supports mostly linear models and is well suited for supervised learning. We have used this tool with great success in many Kaggle competitions. It is especially useful for very large data sets. It is a very powerful tool with high performance.
And it is also important to add that it is pretty good for prototyping. So if you have a big data challenge, then online machine learning models you can use them on your laptop. It will take some time, but you don't need to load whole data sets in one time. So that's why online learning is also very useful for R&D teams which are not able to use cluster.
Yes, one very common use case for this is natural language processing, where we want to vectorize very large corpora of text. Then such a tool is priceless, basically, because it enables us to process data sets that would otherwise be impossible to process. Okay, so I've described two techniques, but there is a general problem on how to score good results in a machine learning problem or task. And I will leave this one to Peter.
Okay, thanks, Mike. So behind this question, there is an interesting, funny story. Before this presentation, we did a voting in our company, so engineers were submitting different topics which they would like us to cover during this speech. And this question won the voting. I was surprised. But let me try to answer that. The first answer is relatively easy, but implementation of this, this advice is harder. So basically, what to do to score good result on Kaggle or to build good model, machine learning model? You need to try many algorithms with different parameters and combine them with different data transformations. And this data transformation part is even more important. And then, once you check many combinations, it is very important to be able to judge which one is best one. So basically, data scientists on daily basis is exploring this space. For if he has a problem, there is a set of transformations which he can do on the data. There is a set of algorithms. There is more and more algorithms, right, coming from the research. And each algorithm has different set of parameters, and his job is to find the best parameters. And we are doing that all the time, and it became a little bit boring for us. So we start thinking about automating this process. So let me share with you a secret weapon of our Kaggle team. So we said that, okay, let's use technology. Instead of our time, our data scientist time, let's move the cost to the technology. So what we did? We started thinking about this problem of selecting proper data transformation, proper algorithm, and proper parameters, as it would be optimization problem. So classical optimization problem is a problem where you have a set of objects. You have a kind of target function which takes object and produces some score, and your goal is to find the object with the best score. And you can read, you probably know a lot of algorithms they are not machine learning algorithms, which can solve optimization problem. We decided to use genetic algorithm. But in this case, to check the score of, the first question is what is the score of such object, of combination of data transformation, algorithm and its parameters, we decided that it would be cross-validation error. So we know that to compute that, it involves a lot of processing, computational power. So this kind of meta-algorithm, genetic algorithm, which explores the space of different transformations and machine learning models would not work on a single machine. So for that, we decided that we'll use Hadoop. And the goal of this tool was to produce a report for data scientists, which give him insight what kind of data transformations, what kind of algorithm are the best or are most promising for particular data set and problem. So here is an example of such result. Here we checked 3 algorithms, and here you can see their performance. On the x-axis you see train error, on the y-axis you see cross-validation error. So the best models are here. So for these data sets, random forest algorithms are performing in the best way. And right now I would like to share with you...
Maybe just one remark that we measured not only cross-validation and test error, but also training time and which data variant produced the best results. So we gathered a lot of data and we wanted to include all this data into a visual summary.
Yeah, it was only the beginning, the first step which we did with the problem, just to know in which direction should we follow. And right now I would like to share with you the architecture behind this tool. We did it around 8 months ago as a POC. So because of that we decided that we'll use Python, which is pretty good for prototyping. Python has a really powerful library, scikit-learn, which is very good for such problems. And what? For the right hand, on the right hand side, you see the Hadoop cluster. So to spawn some processing in the cluster, we use Yarn. So basically we deployed some worker processes via Yarn on the cluster. They were communicating with orchestrator process, which was running the genetic algorithm. The communication was done via RapidMQ and Celery as a message broker. Results were stored in Cassandra. We decided to use Cassandra basically because of flexibility in data format. Those algorithms has different parameters, and it was easy in this way, to store every parameter as it is. And as a web interface, we use Django, which is extremely popular, and most of you know about it. But as you might suspect, this architecture has some significant limitations. And first limitation is limitation of scikit-learn, which doesn't support distribution of training one machine learning model. So you can train one model on one machine. And it is a problem. For some algorithms it works, but for more sophisticated algorithms like neural networks, it will be showstopper. Second, very important limitation of this architecture is a problem with data transformations. It is very hard to produce a finite state of transformations which can cover all potential data sets and machine learning problems. Every time in practice you need to combine with a new transformation which is specific for a particular problem. So to solve those problems, I just want to add one more thing before I go to the next slide. This tool was used internally, but the next step we decided that we'll make a product which will be open with better architecture, and the product name is DS Studio. It is still under development. And here we decided that for machine learning computation we will use Spark instead of scikit-learn. And we decided to create a pretty simple web graphical interface which allows us to produce data transformations without need of writing a code. And this tool is called DS Studio, and if you want to hear more about it, we would like to invite you to our booth and we can share more information about it with you. Okay, so it is everything what we wanted to tell you today. Thank you for coming, and we are waiting for your questions. Thank you.
So does anyone have any questions?
Yes?
Okay. The question was, can we share any actual algorithms that we used?
Hashing.
Hashing.
For hash trick.
So you mean hashing algorithms. Well, actually, the tool that we mostly used for the hash trick is Waubit, and we have used the set of hashing algorithms that is available there. I'm not entirely sure what their names are, but there is a variety of hashing algorithms that are well suited for text data. So
I can tell you what is the simplest algorithm for that, which will work for sure. It's basically you need to transform characters to their ASCII representation. So right now we have numbers. You have numbers, and what you basically do, you count a sum where you multiply the value of character by some big prime number, which is increased to you count it by power of k, where k is position of character. So we have prime number multiplied by character value in ASCII, and you need to raise the prime number to the power of k, where k is a position of character. And you do the sum of that and count the modulo value, modulo k. A k is the range which you want to reduce this space, and it will work.
So that's a pretty generic hashing algorithm, so nothing special is needed for the hash trick.
I am pretty sure that this algorithm has a name, but I just don't remember. I know that everyone in ICMICPC contest use it, and it works just fine.
Okay, thank you for the question. Are there any? Yes?
Yes?
Can you talk a little bit about the transformations that you consider? Do you use logs? Are you normalizing? What are the most common?
Yes, in the first version of the tool, we used, first of all, we tried normalization. We tried taking logarithms of the features. We tried taking squares of the features. We tried introducing interactions, so multiplying one feature by another. What else we did? We also tried genetic algorithms for feature generation. So basically, we constructed a formula based on crossovers between a previous generation of the formulas. So that's one approach that we have tried. It worked fine with some approaches. For some, it didn't work at all.
It's still very heavy in terms of computation to produce data transformations automatically.
So the
it's
difficulty,
doable, but
the difficulty with creating a set of transformations that would work with every problem is the thing that led us partially to the second version of our platform, where we can easily create a custom transformation that's tailored for a particular problem by moving blocks around and just connecting them with arrows. So that's one functionality that we included in DS Studio.
So for most of those algorithms, you really are just interested in hopefully predicting well, because once you do a lot of those transformations, a lot of the your interpretability of why you would do that maybe goes away.
Well, yeah, but the interpretability is lost not only because of transformations, but some of the algorithms are not interpretable at all.
Sure.
So when you want to use deep neural networks or a random forest, for instance, you have already lost the interpretability of your model.
So it will not work if you need to understand why this model works in this way.
But we agree that for some applications, interpretability is very important. For instance, in finance, financial analysts would like to know why such a score is generated. And yes, it is a very general problem in machine learning that at some point when you want to tune your result, you use the interpretability.
Yes? Formulas? Okay, so this is train error, this root mean square error, and here is cross validation, root mean square error. So the target function which you are optimizing depends on your problem. Here we had a problem where we were trying to find a minimum of models of root mean square error. Yes?
I think I know the answer, but what's your general heuristics for figuring out the model order for a more general problem? Like, for instance, in your English language case, figuring out ballpark area for the K. I think most of us have an insight, but for a more general problem, it doesn't often jump out at you.
I'm not sure I got your...
It's the number of features you need to, in the example that you gave, you needed to sort of select K, which was the number of words you're going to use in your hash.
Oh, it is not.
In general, that's not an easy thing.
It is not true that it is number of words which we are going to use. It's number of cubics.
Yeah. Okay. Yeah, but features, order. Yeah, but in general, that doesn't necessarily always jump out at you.
Yeah, you're correct. You're absolutely correct. So what we did is that we used cross-validation for this, and we trained a bunch of different models with different Ks, and then we picked one with lowest cross-validation error.
So the model order then has to be one of the parameters in
Yes, it is basic. The K becomes one of the parameters that you need to tune. So it is subjected to hyperparameter tuning. It is one of the parameters. So yes, it may be considered as a disadvantage that you introduced another degree of freedom, but you deal with it like with all the other degrees of freedom.
Manually, you have to do it anyway. So there is no magic. We just wanted to optimize data science work.
Thank you for the question. Okay, if there are no more questions, then thank you again for coming and hope we meet at our booth.